Hello everyone. In this video, I'm going to present one of my graduate projects that I did for my neural network class. It was an image classification project called Dog Breed Identification. The goal of this project was to implement a deep learning algorithm to categorize images of dogs according to their breed by implementing Python coding. To accomplish this task and achieve as much accuracy as possible, at first, the data has been pre-processed using standard normalization. Then CNN or convolutional neural network has been implemented as the deep learning model, including different variants of CNN, mainly exception and inception, which I will talk in detail. And then to fine-tune the model, the number of layers before the output, which was a hyperparameter, has been determined depending on the validation set accuracy. Next, augmentation of the data has been attempted as a regularization technique to improve the accuracy of the classifier. The final goal was to enter the results in the Kaggle competition. Now, Kaggle is a platform for predictive modeling and analytics competitions in which statisticians and data miners compete to produce the best models for predicting and describing the data sets uploaded by various companies and users. Towards the end of the project, I will present the scores of the competition as well. So about the dataset, this dataset was used for this project contains images of 120 breeds of dog from all over the world. It was created by a team at Stanford University, and the dataset has been referenced towards the end of this presentation. They built this dataset using the ImageNet dataset to accomplish fine-grained image categorization. The data has around 20,580 images for this project. This is the division of images for test set, train set, and validation set. So two kinds of pre-processing I have done for this project for the data. The first one is normalization. So why do we need normalization? So if the input training vectors are not normalized, the ranges of distributions of the feature values become different for each feature, and thus the learning rate tends to cause corrections in each dimension that differ from one another. This is why the images from from the data set have been normalized to keep in a range between -1 and 1. This is the formula that has been used. I'm not going to go into too much detail, but I just wanted to mention that. The second one is resizing the images. The images in this data set have very different sizes, which is not not an ideal thing for a deep learning algorithm. The images have been resized to a pixel size of 299 because the CNN that we're using, which are exception and inception network, accepts the input size of 299. And to accomplish this, the resize function from OpenCV library has been implemented directly. So let's talk about the baseline model of this project. So for image classification problems, CNN is the most popular choice in the world of machine learning. CNN has some unique characteristics that works in advantage for images. It consists of several different kernels containing randomly initialized trainable parameters based on the depth and filters of each layer of network. These kernels can convolve spatially on a given input volume, starting with the image as an input. As a result, they create some features or activation maps at each layer. These high number of filters essentially learn to capture spatial features from the input volumes based on the learned magnitude. Thus, they can successfully boil down a given image into a highly abstracted representation, which is easy for predicting. In this project, CNN has been chosen as the main idea for the algorithm. This is why. Now, let's talk about the baseline model that I have created. So for this particular data set, there are not enough samples to train a deep neural network like CNN. Furthermore, due to the limitations of computation power available, implementing a complicated deep learning network from top to bottom is also not feasible. So after a lot of online research, the most feasible solution for this project was found in an article which was written by Kirill Panarin, that I've referenced in this presentation as well towards the end, who has used an already pre-trained neural network. This idea has been implemented for this project. So now I'm not gonna go into detail about what exception network is. That could take another week or so. But just to introduce what it is, so exception network is a special variation of CNN that was published by Google in 2016. It is a modified version of the inception network where they are using the depth-wise, something called depth-wise separable convolution instead of inception modules. So for this project, the base model is to utilize the pre-trained weights from the exception network and implement additional fully connected networks, fully connected layers with softmax on top of them. This approach with training a pre-trained model with a classification head attached to it in smaller data set is called transfer learning. The images are fed into the pre-trained weights from the exception network, and the output goes through the fully connected networks. Finally, the softmax gives the probability of an image belonging to each of the 120 classes, and the cross-entropy error is calculated towards the end. This idea of transfer learning works very well for images because the bottom layers of a deep learning network, a neural network trained on a large data set, extract low-level primitive features of an image. These are the basic features that all images have, for example, contours and simple shapes. These common features are applicable for any image, and therefore they can be transferred to any image classification problem. Thus, without wasting computation power to learn common features, transfer learning works beautifully to learn high-level features of images and shows tremendous performance. So the initial validation accuracy using the baseline model that I showed you in the previous slide was achieved, was around 82% validation, and the TensorBoard result is shown here. In here, we can see the training accuracy is around 99%, and in here you can see the validation accuracy. The two graphs on the right are cross-entropy errors and losses, marked as losses. I'm not going to go into too much detail. I just want to focus on the validation accuracy and the training accuracy here. So after doing this, started my trials for improving the performance. So these are the main three steps I have taken. I have played around with them, and I'm going to go over them one by one. So the first one is changing the hyperparameter, which is the number of hidden layers. So initially, as shown in this figure, only one fully connected layer was implemented before the softmax output, right here, which gave us a validation accuracy of 82%. So in order to improve the number of hidden layers was increased from 1 to 2. However, the results showed that adding one more layer decreased the validation accuracy to 79%, as shown here. Where blue is the 2 hidden layer performance, which is lower than this gray one, which is 1 hidden layer. So after comparing this performance, it was obvious that sticking with one fully connected hidden layer was the best solution for this one. And all the work done after this point was implementing using only one hidden layer. Also, a great lesson I have learned is that complicating the structure does not always necessarily mean improving the performance for deep neural network. So the regularization techniques, the first one I tried is the early stopping, which is one of the most common regularization techniques. As shown in the graph here, the validation error starts to decrease around 14 epochs. Therefore, it is a good idea to stop training the data set around this point, because beyond this point, the network will start to overfit the training data and the performance will start to go down. So 14 epochs was determined to be the early stopping point. The second regularization I have tried is data augmentation. I have spent a huge amount of time on this. So data augmentation is one of the most common techniques of image classification. Regularization technique. The goal of regularization technique is to increase the size of the training data set as much as possible. And for this project, I've done 3 kinds of augmentation on the training data. The augmentations were implemented using the OpenCV get rotation matrix function. So the first augmentation was rotation, a random uniform rotation of images between -20 degrees to 20 degrees. And as you can see in the image, this image shows the rotation part clearly. The second one is the translation, randomly and uniformly shifting or translating the images between the given range that you can see here. And in this image, you can clearly see that the image has been shifted to the right a significant amount. And the last one was scaling. The scaling is to randomly and uniformly scale, which means zooming in and out the image between the range of 85% to 125%. And this image clearly shows that this image has been zoomed in. Now, results of the augmentation, but unfortunately, the validation accuracy did not have any significant improvement after the augmentation. As you can see here, it actually goes down for some reason. The training accuracy did not improve, and so didn't. The validation accuracy did not improve as well. After a lot of research, the most probable reason seemed to me to be too much augmentation. So I tried to reduce the magnitude of each augmentation parameter. For example, instead of 20 degree, I put 5 degree. I tried 5 degree, but that didn't help as well. The validation accuracy did not improve. So the lesson here was that augmentation needs a lot more further work to yield improvement. But it was great to be able to actually implement some common augmentation technique, and I was able to play with them. So the third and final improvement that I have done is actually coming up with a new model. After trying many regularization attempts, I decided to change the baseline model for this project and add another network along with exception. And for this, the Inception v3 network has been implemented, which was published in 2015. The idea was to concatenate the pre-trained weights from both exception and Inception network and use those weights on DocBreed dataset to train them. As you can see that we get 4,096 feature vectors after concatenating. And then the images are trained over those features with the custom fully connected layers, followed by the softmax layer and the cross entropy calculation, like before. After running through this base model, I was finally able to achieve a validation accuracy of around 85%, which is a significant improvement upon the previous attempt. The results from TensorBoard are shown here. This is the final accuracy achieved from all the trials and errors attempted for this project. And, well, it was quite satisfactory for a beginner like me, I would say. So towards the end, I wanted to evaluate a few useful performance metrics. One of them was the F1 score. As you can see, also the precision and the precision and recall as well. The average precision was 85%, which means when the result claims that a dog belongs to a specific breed, it is right 85% of the time. And the recall value means the classifier can identify 85% of the dog breeds. Another one was the confusion matrix. The main concept is to count the number of instances an image is classified. Each row in a confusion matrix represents an actual class, while each column represents a predicted class. A perfect classifier would have only true positives and true negatives. So its confusion matrix would have non-zero values on its main diagonals. And as you can see from this confusion matrix here, that most of the brighter cells lie on the diagonal, which means the classifier has classified most of the dog breeds correctly. Finally, this is the result of the Kaggle competition. Our team of 2 members was ranked 327, which was again quite satisfactory for the first time neural network learners like us. So here are the references that I have used for this project, if you need them. So this project was my gateway to learn about the cutting-edge network architectures of today's machine learning world. Overall, this project gave me a successful overview of how to implement a deep neural network for a practical classification application like dog breed identification. I'm so glad I got to share this project experience with you all, and as always, thank you for watching.